So our first thing after the introduction is some of these nitty-gritty details of Julia with the syntax and the features, but which are important for performance code. You need to understand how Julia is working to make it run efficiently. And I have prepared these slides that have all of the examples, but I'm actually using the notebook, which also have the basically the same examples. Let me, okay. So this will be, if you already know Julia, maybe you will, it's like a refresher. If you're not that knowledgeable in Julia, hopefully you can then see some of the features, and you can always interrupt me if something is unclear. So first, yes? Um, Pardon?
You describe the folder what is presentation.
Yes, exactly. So it's in presentations, then it's 02 fundamentals and examples, and they are the notebooks. One very important thing in Julia is the type system. So we know Julia is dynamically typed, and variables can change the types. So the type changes depending on the value that you assign. So we can have a 1.0, and then the type is a float, 64, or we can have just a 1, and then it's an int 64. You can also fix the type at the declaration, and then it is fixed, and there will be an error if you want to assign a different type value to the variable. And you can also have global variables in Julia, but these are, from the performance perspective, a little bit problematic because of the type. If it's dynamically typed, you will see it later also. Then it has to always evaluate which type the global variable has. So you can use constant global variables and also assign the type. And then it will always have this constant value, which is good for the performance. In these notebooks or in the interactive Julia, you can override the values of a const variable. However, in normal Julia code, if you run it as a script, this is not possible, and you will get an error. Julia is using a type hierarchy. Therefore, we can see that float 64 has a supertype of abstract float, and then it goes on to the real and number, and then we have at the top of the type hierarchy any. Therefore, any is the supertype of itself. So this is basically the root of the complete type hierarchy. We can also check if type is a subtype of a different type. So a real would be a number, but it's also a subtype of any. And every type is a subtype of any. And Julia has the Julia types can be concrete or abstract. And in this case, the float 64 type is a concrete type. Therefore, we can have actual values of this type. And abstract types are only used for the type hierarchy and for the generic programming features of Julia. We can also have parametric types. And this means that you have a type that is dependent on a different type. For example, this complex type is not a concrete type, but if we give it a float 64 type parameter, then the complex float 64 becomes a real type that can be that can have a value. And you can always find out more about the type in the documentation with the add doc macro and the type. And then we see here a nice explanation how the array type is actually a parameterized type that has a supertype and abstract array. And here also for the n tuple, where we see it's the one is the length of the tuple, how many elements are inside of a tuple, and the other parameter is then the type of the tuple. So here we see a graph of these types. So the most of these types here on the top are just for the hierarchy. So these are the abstract types. And then we have our concrete types at the bottom, our complex type, float 16, in 32, and so on. And our complex type is a little bit in between. It's not an abstract type, but it's also not a concrete type. It's a parameterized type. There is a special, I'm sorry, it's jumping. There's a special value called nothing. In this function, you can test. It has an input parameter of x, and you don't specify the type of x. And if you test it with larger than 3, the input value, then you return the value itself. Else you return the special value called nothing, which then says that nothing is returned. And if we check what is the return type of our function, we can use this return types predefined function in our base package. Then we see it is any, because our input type is not defined. Therefore, we never limited the types that go inside of this function. So we can give it any typed value. Therefore, the function itself doesn't have a type. But we can also specify an input type for our function if we use return types. And then it says what are the possible types that can be returned by this function, because Julia always checks during the processing of the function, during the compilation, it needs to check the types. And so it sees it's if I'm entering a tab in in64 as an input type to our function, then it will either return nothing or in64. Therefore, Julia is analyzing statically the code and then can derive that depending on what kind of input type you have, it will have the same type returned or this nothing type. Yes, please. This is just the expectation of the return types function, because if you have a function, it can have multiple parameters, and these multiple parameters can have different types. Therefore, this is just a function with one parameter, so you only have a tuple with one value, a type in 64, and if it would be if it would have multiple parameters, then it could be in 64, float 64, depending on the types of the input parameters that you give the function. So we have this special type nothing where it only has one value, nothing. And we see that we can also have unions, and then unions represent a set of types. In this case, of the possible types that can be returned. And we see, okay, nothing is just a value of the type nothing. For the control flows, Julia has these begin-end blocks. As we see here, you can also write them in just one line with a semicolon in between. And it has the normal if-else blocks, and you also have the else-if block to have multiple conditions in your control structure. You can also have these short circuit expressions that basically says only if this condition is true, then also F will be executed. As in this case, G is only executed if the condition is wrong. And we have ternary expressions, as you know from other programming languages. So this is the condition, and if it's true, then this is executed, and else this is executed. Then we have our typical loops with while loops and for loops, and you can have in the for loop your iterator variables and then iterate over a range or over some kind of collection, like an array or a vector. So with ranges, you can also have steps in the ranges. And we can see this is then an element of step range. You could think of it like a generator in Python. But if you want to actually have all of them collected, you can use this collect method from Julia to generate an array out of your range. You can also have multiple iterator variables combined in a for loop. Or here in this case, not use ranges, but have them iterate over these arrays. Now to something a little bit more well, interesting. Functions in Julia are one of the main structures in Julia to express your ideas. So you know the function end syntax. You can also have a one-line syntax to define your function, and then this the return value is just the expression here on the right side of the assignment. And we can, in this case, you see that the same function can have multiple parameters. And then these are called the methods for this function. Therefore, you can have one basic idea of functionality, for example, a sum or a multiplication, and express it with multiple implementations and have different parameters and parameter types for these implementations. And these are then called methods. So these are all methods of the function f. And if you ask what are the methods of f, you see here all of the all of these implementations. And we can also see the return types from these methods. We can also have anonymous functions. There we don't give it a name, but we can still assign it to a variable. So Julia is a functional language, and functions can be used as objects and assigned and passed down to other functions. In this case, we have this filter functionality which iterates over an array and then uses the passed function to filter the elements. So in this case, we have a condition. It compares the element with 2, and then the filter function is calling our function, and we are passing it a function object. Then we've already seen the tuples. Tuples are immutable collections of values with constant number. And this will play a role later on for the performance, because here, because of the type of the tuple, Julia always has the guarantee for a tuple. It will always have 3 elements, and you can't change them. So we again see this tuple type here. So it's a tuple with 3 elements with int64, float64, and string types. And you can get the value out of the tuple, but you can't assign a value to the tuple. So it's not immutable. However, what you can do is, if you have a mutable value inside of your tuple, then you can change this value inside of the tuple. For example, you have a tuple with multiple arrays, then you can change some of the values inside of the array, because the array itself is then again changeable. But the tuple, you can't reassign a value. What you can do is you can create a new tuple and then use some of the values and define some new values. And you can use these tuples, if they're returned from a function, they can be destructured to multiple variables. And as we've seen, the tuples or the tuple type is used to express the function signatures. So one of the important language attributes of Julia is multiple dispatch. So what does it mean? I think I have a nice slide about this. So single dispatch from languages that are using object-oriented programming. There, the function that you execute depends on one of its parameters, which is the first parameter. So if you have some kind of object and then call a function, it will check which type has this object, and then it knows which function to call. So actually the function is basically defined as the class of my object, and then the types of the other parameters. So it's and then it decides according to the type of the first so the first type, which function to choose. And with multiple dispatch, it's different. There, it always checks the types of all parameters to choose which method to execute. Okay. So for example, here with our multiplication, we have a multiplication of two float values. And here we have a multiplication of a float value and an integer. And in both cases, it returns a float. And now if we check on the which method is called for the multiplication, if we have two floats, then we see it's using this method with parameterized types, where we have either float 16, float 32, or float 64, and both of our parameters have the same type. And if we do it for integers, it's a different implementation where both parameters have one of these integer types. And now if we have a float and integer, we see it actually uses a different implementation. It's using this promotion of our input parameter types, which is done by this method implemented in Julia, which then takes some arbitrary values from number types. For example, floated integers are both in the type hierarchy numbers. And then this implementation checks how to promote the values so they can be, so the multiplication can be applied to, or to have a fitting implementation. For example, promote the integer to a float, and then you can again use the previous function where both parameters are floats. So we see, depending on the parameter types, and it depends on both parameter types, a different method is chosen. There we also run a little problem. Here we have a function where we don't specify a type for the parameters, so they are both any. And we have a method for f where we expect both parameters to be float. And this also works. If I give it two floats, then this implementation is executed. If I pass it a string and a float, then this generic method is chosen, because then it looks at a fitting method, a fitting implementation for f function. It sees it's a string and a float, and the float will not work. Then Julia has to choose this any method to execute the f function. And now we have this interesting ambiguity case here. If we have our a and b function with this method where we have float and any, and then any and float, and we actually pass it to floats, then we will run into an error, because Julia can't decide for you which implementation it should execute. Is it the float any or the any float? Because we don't have a float implementation, and there is so there's an ambiguity in the decision which method to execute. And we can think of two solutions. We can have a float implementation, or an any implementation that catches all combinations of parameter types. And in this case, it then calls the both float implementation, because this is more specific to the types that we passed to the function. Therefore, there's no reason to go higher to the any implementation, because this is then a more implementation more specific to our input types. So this is an integral part of the Julia typing system, and this is useful for many things. So one thing is that if you have different types and you can have a generic implementation of your function, for example, a sum, where you can say, okay, there are some things that I want to sum up. Then I will just do the natural thing and iterate over it and sum it up. But if you have a more specific implementation, if you know, okay, for these specific parameters, I know I can make it have a more performant implementation. Then you can specify the same function name with different parameter types, and then Julia can choose the more performant implementation because then you can specify the more specific types, and then Julia can make the implementation more performant by have more specialized implementation. You can if you specify your own constructs, for example, there is some type missing, then you can create a new type, and then this is also interesting if you for different packages where the types overlap, and then Julia is able to use more generic implementations for new types that are still adhering to some interface, to some common type that you also use. So you basically say, okay, this is a special number, but it's still just a number. And then Julia will, for example, use then some kind of algorithm that uses multiplication. Then you can just implement multiplication for your new type, but then just use a generic algorithm to apply to your new type. And this way also many packages overlap in their types, and then you will get a surprisingly functional, well package ecosystem where many types that are defined in different or in algorithms that are defined in different packages, if they're well defined in the type specifications of the input parameters, then they can basically fit well and then use the algorithms from some other packages. So this is another interesting advantage that surprisingly works if sometimes there are conflicts, but often it works. And we've seen these your manual implementations by defining the new methods. And Julia is also using something called specialization, where Julia uses the input parameter types to infer the variable types and then produce optimized code. For example, here we have our test function. We just use multiplication, and in a generic implementation, if you would then think about what is the compiler producing, then it would always need to check what kind of type has X, because it does need to know this than to call the multiplication. So in the most generic thing, the implementation of this would be, hey, before I can do this multiplication, I first need to check what is the type, and then I can call this multiplication. And we see here that if Okay. Julia, if it's optimizing your functions by looking at the types, and if you pass it a certain type, for example, an int64 or a float64, it then already knows which multiplication to choose. Therefore, it can produce these specializations. So as we see later, Julia is doing something called just ahead of time compilation. Therefore, if you have your Julia code and you call the function just before calling this function, Julia checks, okay, what are the input parameters? And then it uses the low-level code that is actually executed on your machine. And depending on your input type, Julia can then derive optimized code by looking at the type. So if it's an int64, it knows the multiplication will always be the int64 multiplication. And if I'm using a float 64, then a different multiplication is used. And then it can cache these specialized compilation results for your function. Thing I played around yesterday. So it doesn't show the methods, but it's producing the optimized, specialized versions of your methods. And in our case, for the multiplication, it then uses the if it's a float 64 input parameter, it uses the float version. If it's a int64, it's and float 64 version then of the multiplication, it then uses the more generic one. And this is then already baked inside of this compilation. Therefore, if you next time call the method with your with specific parameters, and it's already compiled, then Julia can use this already compiled and optimized version with this combination of input parameters, input parameter types. Okay, let me check. I think I'm a little bit lost on the okay. And we can see how this automatic specialization can be very useful. If we look at this example of Mandelbrot let me reset this. Okay, if your kernel, this is for demonstration purposes, if the Julia kernel kind of gets stuck, you can restart the kernel, and then the Julia instance in the background will restart, and then your notebook will reconnect to the newly kernel, and you will see here on the bottom, it says again idle, and then the kernel is restarted, but then it basically forgot what you did in the cells. So if you define some variables, you need to evaluate the cells. Now for the Mandelbrot, the Mandelbrot set, we have here an implementation where we take one as parameters the position in the Mandelbrot set, and then compute the image with a certain distance. And here I have the implementation, and the implementation itself is here, and there are no input types defined here. So it just assumes there are some kind of types and then applies this Mandelbrot algorithm to these values. And it finds out, depending on with what you call it, what will happen. And in our case, we first call it with a float 16 parameter values. Therefore, our x and y coordinates are float 16 and also our width. So the width is basically the area that we want to produce. And we see I can zoom in by reducing the width here, and we can zoom in. So I'm pressing Shift Enter to reevaluate the cell and generate this picture. And as we see here, at some point, it gets blocky because the precision of our type is not enough. And then we can easily change it to a different type with a higher precision, float 32. And now it's working again. Therefore, this same generic algorithm can be applied to different types. This is a nice example where by using different precision of the types, we can go further depending on how far we want to go in our, or what kind of precision and what kind of type is necessary for our computation. And the algorithm will still work. And after float 32, at a certain zoom in again, we can then change it to a different type, and then it will be fine again, because it then uses the same algorithm with a higher precision type. And we can see I did not re-implement this algorithm for a different type, but Julia generated these specializations. And we see it generated one for float 16, float 32, float 64, because I already called it once with these types, and then it generated this compilation. And now, if it's called again with this type, it can go in the cache and see I already did the work, the optimization, and then run the optimized version. Can also check here on the precision. If these 53 precision bits are not enough, we can even go to big float, but then this implementation is different. It can use an arbitrary precision that we can also set, but then it's a more complicated process and it will take longer than these normal float 64 float types. And internally, a complex type is used for the calculation of the Mandelbrot set. And here it automatically then uses the type of the input parameter to create this dependent type of this complex float 16 in the further down in the algorithm of our Mandelbrot set. So this is a nice example of a generic algorithm where we can pass different types, and Julia will then do the right thing and use these types and generate an optimized version. On the other hand, if you want to make it work with different types, then we have to keep in mind what do these types have to bring. So what kind of what kind of interface do they have to implement? So in this vector dot implementation, so it's just an element multiplication of the elements in a vector. We can say we need to use we need to check on the type because we need a 0 element. Therefore, for example, we use the element type of our A parameter, and then the types also have to implement each index function because we are using it to iterate over these collections, basically over this vector. Therefore, our types also have to implement this. And then the multiplication also then depends automatically on the type of the elements in our vector. Now the question would be, what is the what type will be C? And here we say we initialized it with the type of our A vector. Now if we execute it with int vector and a float vector, then our result will be a float because they have to be multiplied, and then our result will be floats. But if we ask Julia what is the return type of the function, it says it's a union of float 64 and int 64. So why is that? If Julia is doing the statistical analysis of the function, it sees we have this type of C, and then we are iterating over the vectors. However, it could also be that we never go into the loop because the vectors are empty. Therefore, C gets never promoted from an integer type in our case, of the first vector type to a float. So it stays an integer. Or it could also go into the loop, and then C gets overwritten with a float type, and then we would return a float type. Therefore, and this is actually a problem in Julia from performance-wise, because this means that our function is type unstable. This means it's not sure which return type a function has. And the more possibilities there are in the types, the less performant code Julia can generate, because it has to check for all of the possibilities of types. And we can, how can we fix it? For example, in this case, in this implementation, we narrow down our interface for our function and say it both have to be abstract vector types and both have to have the same type of the same number. And then even if we then try to pass it to vectors of different types, then there will be an error because it does not fulfill our interface here. Therefore, there are possibilities in for the generic implementation to make it more type stable and to check on the types and to have some guarantees in what types are used for our values while still have an abstract interface.
Hello?
Yes.
Yes, I have a question regarding this example that you showed with vector dot two. So in this case, would it be what if, for example, in my application, I only want to work with the vectors of float 64s, and then I specify that A and B should both be vectors of float 64s. Would that be preferable to what you showed here with abstract vector?
It really depends on what you want to allow for your function. It's your function or your method,
Mhm.
and
Mhm.
if you want to have a very specialized function, you can do it. And if you want to have it more a more generic algorithm that works with
Mhm.
any type, and you don't really care about the type, you just care about a good generic implementation, then
Mhm.
you can have it more generic. And
Mhm. Okay.
maybe it also depends on if you want to have a more generic version because you're writing a library for someone else, and then you want to have
Mhm.
it nicer and more compatible to other things because you want to have a nice algorithm. You have an
Mhm.
algorithm library, and then you want to have it work with many different types.
Mhm.
If
Okay.
if it's just in your little toolbox for your own code, then you can do whatever you want. You just have
Okay.
to then think about the performance.
Okay. But like, does it imply that if I have if I specify the method for Float64s, does that automatically mean that we have better performance compared to abstract vector T?
Um, Not necessarily, because
Okay.
if, as we've seen with the specialization, you can have
Mhm.
an abstract or generic implementation, and when Julia encounters, if you call uh, the function, it will um, it will check on the input types. It will choose an implementation, a method, and then it will do an optimization and create a specialization. Then it would generate a
Mhm.
specialized version where it is optimized for float. And then this
Mhm.
would be more or less the same as if you would
So-
narrowed it down to floats.
Okay. Okay. Thank you very much.
Yeah, you're welcome. Okay. Yes, if you open up a notebook and it asks for the kernel, then just select the Julia 1.11.5 kernel. Um, Another thing that you will also need for the exercises, structs. So structs are basically collections of or a composite type. So it's a type that consists of values of different other types. In this case, we have our struct X, and we have an A, B, C, and the A is of type any because I did not specify any type. So I can put anything there. Then I have the B is a number, and the C is a vector of type any. So I can put a string in here, a float, and a vector of 1, 2. But as we see here, structs are also immutable by default, but you can also specify them mutable. And this is also kind of a performance thing that you can change this or define if it's mutable or immutable. For Julia in the optimization, it's if it's immutable, then it can do different things with the memory allocation, as we will see later, also tomorrow. So there are pros and cons for mutable and immutable structs. We can, even if our struct itself is immutable, so we can't change the value of one of our members here, we can still um, ch change something inside of our mutable members. So C has a vector, and the vector is mutable type. Therefore, here we can change C, even if our X struct still has this C as a member. So we changed C, but we did not change X. So we see I can do it again. Add another 3, and in our struct, C still points to the vector, but the content of the vector is different. And I can also define the mutable and then change the A value even after I've created Y. So here is an example for a custom struct. This is a one hot vector. A one hot vector is a vector that is empty except for one place. And in this one place, it has a 1. And if we have a vector of a very large size, 50,000, I don't know if it's very large, 50 million, we still only need to store 2 values. This is the length of the vector and the position where we have a 1. So this is a very compact way to store a one hot vector. We only need to know how large it is. We know all of the values are 0 except for the one place where it is a 1. And we can also define these other methods for our new struct. So we define the size, and we can define getIndex. So get me the element at a certain index. It then takes our type and the integer for the index, and then we can return, is it a 1 or a 0, depending on our index. Therefore, we can create our one hot vector, and it can also be printed. And we see we have our new type, and we can implement some methods, and then we can already use our type with existing algorithms. For example, from the linear algebra package, the dot function then will be usable because we just implemented the interface that is necessary for this generic implementation of the dot function. And we see what if we call dot with our 2 one hot vector structs, it will fall back to an abstract array implementation, because I defined my struct as a subtype of an abstract vector. And then this fits in our type hierarchy, this abstract array interface in this dot implementation in the package. Now I can also run it with some vectors. And we see that we have some very large vectors, and we have then some index of our one element that is a 1 in our vector. And we can measure the time that the dot function is using. So these are 9 milliseconds. However, we can do a little bit better because we know that so the normal dot implementation will iterate over all elements, because this is the thing you would do if you do a dot implementation, and you don't know the details about the type themselves, but we can create our own dot implementation where we just check the indices of our 2 one hot vector elements, and then we can measure the time, and it will be way faster than the normal implementation. So by having our specialized knowledge of our one hot vector, we can then create our own specialized version of the dot function that works with our type and is more efficient than the than the generic implementation. And this is then also one example for how the type system supports this. Okay. So the other two topics here are arrays and macros. But we are running a little bit out of time. But this is fine. This is more more of an overview of the different types of arrays, so vectors, matrices, and so on. You see a lot of examples here, how to create the arrays, random with random values, zeros, ones, and so on. So this is also an important thing with the views, but we will talk about it also tomorrow. And reshaping. So this is more of an overview that you can also take a look at yourself. And here in the macros, there's more like a hint that they are very nice macros. For example, the doc. If you're using Julia interactively with the REPL, then you can just use the doc macro and get some information about the definition of these, of whatever you give to the doc macro. Before we go into the next little section about some workflows in Julia, do you have maybe a question before we go into a break? Yes.
One question would be, when would you say is it most crucial to specify which type to use? Because as I understood now, Julia can infer which types are used and therefore will still be quite fast. But for example, in the example of the function with the unstable result, this can also be problematic performance-wise. When would you say is it strictly recommended to specify the types when you do not really need to count?
That's a good question. When should you use the more specific types, and when just use the more generic ones? So in general, you want to use the generic ones or the non-specified ones and let Julia do it, except if you run into performance problem. So also Shin later will we will look at this. You can look at the output of how Julia sees the types and how it infers the types of the variables inside of your function, and then you will see if it's stable or not, or if there's a problem, if there's ambiguities, or if there are if Julia can't decide which type it is, then you can check it, and then you would be more specific to help Julia to generate better code. What else you then would stick to more generic implementation.